Okay, so let's see what we just talked about. So first of all, we have just this part here. Okay, so let's see what we just talked about. So first of all, we have just this part here. You see that? Okay, that's supposed to be green. So we have just that part there, and this was the average rate of change. Uh, this gave us the average rate of change. So we had like T1 was equal to 0 and T2 was equal to 2 when we did that calculation. And we got the average rate of change between 2 seconds and 0 seconds, or between 0 seconds and 2 seconds. Okay, and then we did it between 1 and 2 seconds, and we did it at different intervals. But anyway, this gave us the average rate of change. So this part was the average rate of change. And then we thought, well, what happens if we want to get sort of better and better approximations to what's happening exactly at t equals 2 seconds? And what we thought was, we're going to move T1 closer and closer to 2 and figure out the average rate of change each time. And what that amounts to is taking the limit as T1 approaches T2. As T1 approaches T2. And so we say that the sort of instantaneous rate of change, or the instantaneous speed in this case, but the instantaneous rate of change at 2, or at T2, when T2 equals 2, at 2, is the limit of as T1 approaches T2. And so this whole thing, let's say here, I'll put it yellow, if I can do that, yellow. That is the instantaneous rate of change at T2. And that has a special name, a very special name for us, and that's called the derivative. So I need some more space here, but I'll do it here, I guess. And that is called the derivative. Okay, so the derivative is the instantaneous rate of change, and that's this thing in yellow. Okay, and so we give it a special name also. So if the original function was f, we have a notation for the derivative would be f prime. Okay, and we have various notations actually. We also have dy dx. That's also a notation for the derivative. We also have df of x, or df dx. That's another notation for the derivative. And we also have another notation for the derivative, and that would be like this. Like that. So we have different notations for the derivative of the function f, and we can use all of these. But whatever notation we're going to use, it stands for this thing here in yellow. So we have an example when f is equal to, when I kind of erased it, don't have a lot of room here, but when f of x was equal to 10t squared, or I'm sorry, I should say f of t. I guess this would be f of t here. This would be f of t, and this would be t in our case. But whether we're using x or t, we would change the notations. This would be dy dt, df of t dt, and so on. Anyway, for this particular function, we wrote it out like this. So we could try and calculate this. So let's try that. I need to erase my little, maybe you can't see my little puppy here, but anyway, just erased it. Okay, so let's see if we can do that. So let's suppose we want to do this limit, which is actually the derivative. So, well, let's remember what we usually did is we just replace T1 by T2, because usually we had x approaches a, and we would just replace x by a. Or we had x, for even more concrete, we had x approaches 2, and we would just put in 2. So here we have T1 approaching T2, so we would just put in T2, just like we would just put in 2 for x. Now we're going to put in T2 for T1. So if we do that, what do we get? Put in T2 for T1 means we have to replace this, we have to replace that. And what do we have to replace with? We have to replace them by T2. But then, as we saw many times in many examples, we end up with 0 over 0, which is not so great. So we actually can't just replace, in this particular case, we can't replace x with 2 or x with a, or in this case, T1 with T2. We can't do that. But we saw that maybe we could sort of fiddle around with this and get some answer. So what did we do? Generally what we did, we saw many examples. What we did was we tried to factor the numerator. So if we factor the numerator, first of all, we can take the 10 out. And then we get T2 squared minus T1 squared, which we could write as T2 minus T1 times T2 plus T1, right? We factor the top, and then on the bottom, and I forgot the limit here, so it should be limit. I'm not going to write it out, but you have the limit there. And then here, it's T2 minus T1. So then let me just write it here. The limit, what is it? As T1 approaches T2. Can you read that? Maybe. And then on the top, what can we, and sorry, and then we can do what here? We can cancel this with that. So then we just have 10 T2 plus T1. And then now we can replace T1. This says T1 approaches T2. So now we can replace T1 with T2. And if we do that, we just get 10 T2 plus T2, or 10, 2 times T2. Okay, so we get an answer. And if T2 was actually equal to 2, somehow, somewhere before we said T2 is equal to 2, remember this was equal to 2 because we were talking about T equals 2 seconds. So if T2 was actually equal to 2, we get 10 times 4, or 40. Okay, now what was all this supposed to give us? This was supposed to give us the instantaneous, in this case, the instantaneous speed. In general, the instantaneous rate of change, but in this case, the instantaneous speed. And we just got that the instantaneous speed is supposed to be 40. We did this here, and we got 40. Now, what were the other approximate answers, or the average rates of speed, the average speeds? What did we have before? So I think we had, what were the approximations we had? I think we had 20. That was when we went from T0 to T2, we had 20. And then we went from T1, or T1 equals, T equals 1. And then what did we get? I think we got 30. And I think we got 36 when we went from 1.5 seconds to 2 seconds. I think we got 36. And now we found that the actual so-called instantaneous speed exactly at T equals 2 is equal to 40. So that kind of makes sense. We got 20 as our first approximation, then we got 30 as our next approximation, then we got 36 as our next, and they apparently are approaching 40 because that's what we get. So we say the instantaneous rate of change, or the instantaneous speed, is 40. And this calculation gave it to us. Okay, so, and this is the general form here. And let's write this a little more familiarly as x instead of t. And remember, all of this is called the derivative. So let's write this in a little bit more familiar form. So the limit, and let's not do it at, well, okay, let's do it. As x approaches a. So instead of this approaching this, let's say as x approaches some value of f of x minus, f of, didn't work out right. Well, okay, anyway, T2 is A, so I guess it's f of A minus f of x, usually we write it the other way around, over x minus A. So that's one way to write this. Okay, so let's write this in a more familiar form. So we want to write, instead of f of t, let's use f of x, so that's more familiar. And let's say that the a that this is going to be that we're approaching some a. Let's say that the a is okay, so let's write this in a sort of more familiar context. So instead of using t, let's use the variable x. So instead of f of t1 and f of t2, let's just use f of x. And let's say that, and so this would be x2, and this would be x1, or we'll just generalize it and say instead of x1, let's just call it x. So we'll say x is approaching x2. So that's what we would normally write. But let's call the distance between, or let's call x2 x1 plus h. In other words, we're going to be approaching, here's x2, and here's x1, and x1 is approaching x2, but let's call the distance between x1 and x2, let's call that h. You see that? Sort of. Well, okay, so the distance, I'll write it here. So here's x1, x2, and here's x1, and x1 is approaching x2, and let's call the distance between x1 and x2, let's call that h. You see that now? Yeah. So instead of saying x or x1 approaches x2, let's say the distance between x1 and x2 gets close to 0. So x is moving, and as the distance between them approaches 0, that means x moves towards x2. So instead of saying x moves towards x2. Let's say h gets smaller or h goes to 0. So we're going to make that change. So we're going to say x2 is equal to x plus this h. So x2 equals x plus h. Let's get rid of the 1, just call it x. So x plus h or x1 plus h. And then we can also say that h is equal to x2 minus this x. Okay, so instead of saying that x approaches x2, not a, x approaches x2, we'll say that h approaches 0. So let's write all of this down. So first, I guess we need to write it in terms of x. Let's write it in terms of x's. So we have the limit of f of x2. I'm going to need the space here. Minus f of x1 as x, I'm sorry, over x2 minus x1 as x1 approaches x2. So that's basically the same thing we have here. And then instead of calling it x1, since it's going to be moving, let's call it x and call this x. And then let's do, I'm going to erase these symbols. So then let's do what we just said, which is that we're going to say that x2 equals x plus h. So the distance between x2 and x is h. So if you take x and add h to it, you get to 8x2. And then we can also say that h equals x2 minus x. So if we have x approaching x2, we can, that means the distance between x and x2 is getting smaller. That means h, which is that distance between x2 and x1, is going to 0. So I'm going to now erase this because I don't have much room. And I'm going to erase that. And I'm going to write it with the h's now. So I'm going to rewrite it as the limit as h goes to 0. Instead of x going to x2, the distance between them is going to 0. And I'm going to write, I'm also going to use this expression to put in here. Okay, so I'm going to write, instead of f of x2, I'm going to write f of x plus h. So it's f of x plus h instead of f of x2. And then I'm going to leave this one alone. And then I have x2 minus x1, but that was the distance between x2 and x1, which we said was h. So on the bottom, I'm going to put h. So this is the general expression, instead of using t's and t1 and all of that, and x2 and all of that. This is the general expression for the derivative. So this is the instantaneous rate of change. And we can do this for any function. And if this function stands for the CPI, the CPI means the Consumer Price Index, which is like how much the cost of living. So they talk about the Consumer Price Index increasing or decreasing, means the cost of living is going up or going down. So if this is the CPI, if F is the CPI and X is, say, T, then the CPI is changing over time, then we could calculate the instantaneous rate of change of the CPI. Or, like we did originally, this was the position of a ball falling, and this gave us the average rate of change of the position, or the, I'm sorry, actually it gives us the instantaneous rate of change of the position, and that's called the instantaneous speed. Sometimes we say instantaneous velocity. Okay, but anyway, this is just the general formula, the mathematical formula. You can interpret F in many different problems, but this is the mathematical abstraction of all of those problems, and gives us what we call the instantaneous rate of change, which we also called the derivative. And we had so many different notations for it, like we have f prime, this is f prime, or we have df dx, this is also a notation for this formula, or we have dy dx. All of these are just different notations for this thing, which is the instantaneous rate of change. So let's try and work out this for a specific f. Let's see what we get. Because really we want to try it for many different f's. We want to do this for all kinds of cases, where maybe it's the consumer price index, maybe it's something else. Maybe it represents a ball, maybe it represents electricity, maybe it represents all kinds of different things. But let's say that whatever it represents, let's say that the particular function is f of x equals x squared. And let's find this in this case. Okay, so we're just talking about the math. We're not talking about what it applies to. We're not talking about balls. We're not talking about CPI. Just want to find the math. Then you can use it in all of those cases. So what if f of x equals x squared? So what does this give us? Maybe we can figure this out. Maybe it'll give us like 0 over 0, and we can't even simplify it in any way, and it won't work. Then we're just stuck. But maybe we'll get a nice, simple answer. So let's try and see what we get. So let's write it down. For this case, the limit as h goes to 0 of f of x, but in this case, f of x is there. And so we also need to know what f of x plus h is. So what is f of x plus h when f is equal to that? So it just means you put x plus h in, and you square that, so you get x plus h. And we talked about this before, so you just get that. So now we know what this piece is, and we know what this piece is. That is, we know what this piece is, and we know what this piece is. So let's try it. Let's write it out. So we have to write f of x plus h, which is x plus h squared, and then we write this one. So this is x squared, and then we write h on the bottom. Okay, so we're trying to figure out what the derivative is when f is this particular function, when f is x squared. We don't know what the answer is. We might not be able to find an answer. We can see, for example, when we put in h equals 0, we get 0 on the bottom. Already, that doesn't sound too good. And then, even on the top, we get actually 0 on the top. So that's even worse. So it doesn't look good, but we know from doing this many times, these limit problems, many times that actually, we might be able to work it out. So let's write it over here. So what do we mean by work it out? So we mean expand this and see what happens. So let's try that. So we get x plus h squared. Sorry, let's do it. X plus h squared is what? X squared. Well, let's write the limit first. Limit as h goes to 0. Limit as h goes to 0. And then this is going to be what? X squared plus 2xh plus h squared. X squared plus 2xh plus h squared. So that's the first piece. Then we have to do minus x squared. And then we do h. Okay, so we did that. And then what? Well, if we're hoping something's going to work out better than 0 over 0, we're hoping that we can do something. So what can we do? We can do something. We have here, and we have here, right? And that is, those two cancel. So that's good. Those cancel them. And then we have h here and h squared here and h here. That is, we have an h in each term, so we get to cancel that as well. We cancel that with that, and this becomes just a 1, right? So finally, or not finally, but next we get the limit as h goes to 0 of, now that we've got to do it all to cancel, so we just get 2x plus h. Okay, now, this is a little bit confusing because the variable is not x, or sorry, variable is x, but the thing that's changing is not x in this case, in this limit question. So it's h that is sort of the variable here. So x is sort of, in this case, is considered a constant because it's, in this limit question, x is considered a constant because it's not changing. It's not the thing that's changing. H is the thing that's changing. So we think of x basically as a constant here. So it's like if you just had an 8 here, right, and you ask this limit problem, it would be the limit of a plus h as h goes to 0, and that's just going to give you the 8. Or in this case, this is going to give you the 2x. So let's write that. We got the 2x. So we started with this function, and we said, well, let's just try and find the derivative for this function. You know, this could stand for speed, it could stand for CPI, it could stand for whatever else. You know, there's probably about 5,000 different things it could stand for that people use this calculation for. But whatever it stands for, can we find this thing, which is the instantaneous rate of change, and we get this, 2x. Now, that's a little bit of a weird answer if we go back to the original question, which was this ball falling, and we say, how fast, what's the instantaneous speed? And we get an answer like 2x. That doesn't exactly, that sort of sounds strange. What do you, I want to know how fast the ball is falling. You can't tell me it's falling at the rate of 2x. That's not a number. I want, you know, I want to say, oh, it's falling at 40 meters per second, not some formula, right? So why do we get the 2x here? And why don't we get the 40? Because this is saying, remember, x is like the t, x is the t. So this would be like, in this case, it would be 2t is how fast it's falling. Well, that doesn't make sense either. It's falling at the rate of 2t. No, but what this is this enables us to answer the question for any t. So we wanted to know when t equals 2, and in that case, the answer is going to be 2 times 2, or 4. Now, it doesn't, you know, I didn't use the same original function, so we're not getting, before we got an answer 40, but that's because I had a different, wasn't doing x squared. I was doing a different formula. It was actually 10t squared, or 10x squared. But I didn't do that here. I was just calculating the derivative of this. But anyway, so the answer would be 2t, and so it will tell us the instantaneous rate at any t. So it's better than just getting a number. It's better than getting 40 or 4. We get for any t or for any x, this tells us the instantaneous rate of change, or it tells us the derivative. So we started with this one, and we end up with this. So we were able to do this. We were able to find the derivative for x squared, and it was 2x. So that was nice. Now we could say, okay, let's try it again. Let's try it for x cubed. Why not? We did it once, maybe we could do it again. Maybe we'll get lucky and it'll work again. So then we'd have to change everything. So this would have to be a 3. And then actually this would have to be a 3. And then if we tried h equals 0, we're going to get the same thing. We're going to get 0 minus 0 over 0, no good. Then we'd have to try and simplify, like we did for that case when it was squared. But when we do x plus h cubed, it's going to be much longer. This part is going to be much longer. But, you know, maybe it will simplify or maybe it won't. Anyway, it turns out that it does simplify, and you can work it out. You have to expand this part out here, so it's going to be longer than what we had here. And then you're going to subtract x cubed, and then maybe you can cancel with the h's, and you can actually. And you do all the calculations, and you do this limit, and you finally end up with, if it's x cubed, the answer is going to be 3x squared. So that's, anyway, you should test that out and make sure that it works out. But it does turn out to be 3x squared. And then you could go crazy, say, hey, I'm on a roll here. I mean, it's working, so maybe I should try this. Okay, so you could do that. That's going to be much longer because this is going to be x plus h to the 4th. you're going to really have to expand that out. So this is going to be a much longer piece. And then you're going to, this is going to be x to the fourth. You can subtract that probably, maybe get a cancellation there. And then the h's, maybe they'll get some cancellation. And yeah, it's actually going to work again. So if it's x to the fourth, it's going to turn out to be 4x cubed. And then you start to say, hey, well, I could try x to the fifth and so on, but maybe there's some kind of pattern here. Just because you think there's a pattern doesn't mean there is one, but actually there is a pattern and there is a formula actually. And the formula turns out to be, so you could keep working on these and test out a few more, but the formula turns out to be, I'll erase my important example here, but the formula turns out to be that if it's not, so x squared, what was it? So if f is x squared, the derivative, I'll write it derivative like that. If f is x squared, the derivative, here's this is a prime, was 2x. And if f was x cubed, I didn't do it, but I told you it's going to be 3x squared. And if x was x fourth, it's going to be 4x cubed. And if you keep doing this, there is a pattern, there is a formula. If it's n, it's going to be n, the derivative is going to be n x to the n minus 1. So, for example, here, if n is 4, it's going to be 4x to the 4 minus 1, 4x to the third. And if it's 3, it's going to be 3x to the second, and so on. So that is the general formula. So if this is the original function, then the derivative looks like that. Okay? All right, now we could also try something else. So instead of the original function being x squared, we could try, where I need more space here, I need more space, but I'm going to erase here. So if the original function was not x squared, but suppose it was 5x squared. That was the original function. And you want to find the derivative of that. And we already found the derivative of this one was 2x. Now you might say, well, what's the derivative? Now we're going to say, what's the derivative of this? It's going to turn out that it's just going to be 5 times 2x. So you can just take the derivative of this part and then multiply that times just the 5 to get the derivative. So you don't have to, you just ignore the 5 at first, just do the derivative of this part, which you already did, is 2x, and then you can multiply by 5. And the same thing here. Suppose you had f of x equals, we did this one, x, let's say to the third, we didn't do it, but we said what the answer was, x to the third was 3x squared. Suppose we wanted to know the derivative of this though, not x cubed, but 10x cubed. So it turns out you can just do the derivative of this part, which we already said was 3x squared, and then just multiply that times 10. So the answer would be, the derivative of this would be, I just said it's the derivative of just this part, we know is 3x squared, and then you just multiply that by 10 to get the derivative of this whole thing. So the derivative of this is this. So what we're saying now, from that kind of observation, is, I wish I had this. Okay. Is that if you know the derivative of f of x, so suppose the derivative of f of x is f prime, then if you want to know what the derivative of 10 f of x is, the derivative of 10 f of x is just going to be 10 f prime. So you can sort of take the 10 out and then do just the derivative of f, and that will work. So what we're saying is, using a new notation, remember I said there's many notations, and this is another notation for derivative. So if I want to know what the derivative of 10 f of x is, using this new notation, we can say that it's equal, that you can just take the 10 out, do the derivative of f, and then multiply by 10 at the end. What that means is you take the 10 out, just do the derivative of the f, like that. So we have that rule. Now it's not just true for 10, it's also true for 5. Not just true for 5, it's also true for 2. Not just true for 2, it's also true for -2. And so we can say in general, if it's a constant, it's a constant. Okay? So we have that rule as well. So now we have two rules. We know what to do here for x to the n. By the way, we can rewrite using this notation. We can rewrite this one, or I can write this one as the derivative like this. The derivative of x to the n is nx to the n minus 1. That's what this says. I hope I wrote n minus 1 here somewhere. Like that. So we have this rule, and now we have this rule. Okay, now what if you want to know the derivative of, I'm using this notation, I want to know the derivative of x cubed plus x to the 4th. Okay, so I know how to do x cubed, and I know how to do x to the 4th, but I don't know about this. So I'd have to go through that whole crazy definition that we have up here and do the limits and, well, you know, expand these long things and try and cancel and do all that stuff. Okay, yeah. But the thing is, it turns out that there's an easier way than doing that, because we already know the rule for these individually, and it turns out that you can just do them like this. The derivative of the first one plus the derivative of the second one, like that. Okay, and this is not just true for x cubed and x 4th, but if this was x31 and this was x40, it'd still be true. And in fact, it's true for any functions that you put in here. So in other words, if you know the derivative of the individual functions, let's say you have an f here plus some other g here, and if you knew the derivatives of f and g, you could do this, because this rule that I'm talking about is that the derivative of f plus g, you can just do f first and g. You can do f and g separately and then just add the results. So that's another rule. So that's a third rule. And then actually we have a bunch of other rules as well. And these resembled limit rules that hopefully we talked about. So we have a bunch of derivative rules, and they will help us to calculate derivatives, like we just said, like I just said. So if you wanted to know this, x cubed plus x to the 4th, suppose you had that problem, then you could do it like this plus this. That is, you get 3x squared plus 4x to the 3rd. So you'd have the answer. Okay, you didn't have to go through all of this stuff, expanding it and doing all kinds of limits and stuff. You didn't have to do any limits. You just use this rule.